Hello everyone. In this video, I'm gonna go over basic formulas and prove them before we see normal equation of the cost function. Okay, so normal equation has the matrix form compactly for the cost function and explicitly. Okay, so to derive the normal equation of the cost function explicitly, which is a matrix expression, matrix form, we need to understand the several notations and symbol and formulas. Okay, so first one here, let f be the function from R to the m by m n. Okay, this is m by, so what does that mean? So input is m by n matrix, and output is a single real number. So which means that f is a matrix value function. Okay, so matrix value function. So in vector calculus, we haven't seen the vector value function, right? But this one is a matrix value function. So and then let's say this is the gradient sub a f of a. Okay, so gradient sub a of f means that the take a partial derivative of f with respect to each entry of matrix A. Okay, so the first entry of that one gonna be the partial f over partial a11, and the second entry gonna be partial f over partial a12. Okay, and so on. The last one is a partial f over partial a m by n, mn actually. This is not mn, this is mn, right? So okay, sorry, this is m times n, just m n. Okay, sorry. All right, so now then here's the example. Let's say A is a 2 by 2 matrix, and the f of A is defined by like this. Okay, so you see that input is 2 by 2 matrix, the output is a real number, right? Now let's find out the gradient gradient sub A of f. It's going to be the first entry going to be partial f partial a11, right? So then what? All of other terms going to be gone except for first term, right? Because the first term is the only term having a sub 1 1. So I'll take a derivative of this one with respect to a11. We're going to get 3 half. Right? And then the second entry, to get the second entry, then we take a partial derivative f with respect to a12. Then we get the 2 times 10, 2 times 5 times a12. So you see, okay. So and so on, you can get a22 and a21 for other entry, okay. Then next one, you see, keep in mind this one, okay? Gradient sub A of f. So gradient sub A of f in general, ij component entry of the gradient sub A going to be partial f over partial A sub ij. So next one, trace operator. Okay, so for an n by n matrix A, trace A going to be sum of all of the diagonal entries. Okay, so here to apply the trace to matrix, the matrix must be square matrix. Okay, so the number of row must be equal to number of columns. Okay, here property of trace. Let A times B is on square matrix. Okay, so A is a matrix and B is a matrix. So this is matrix multiplication of A and B. Okay, so let's say A is a m by n matrix, then B must be what? N by m matrix. Okay, then trace AB must be equal to trace BA. Here's a proof. Pretty simple. So trace AB gonna be what? Sigma, double sigma. Okay, so sigma I equals 1 through m, and then another sigma z equals 1 through n, and aij times bji. Okay, so how come? So you see, let's say this is a matrix A. Let's say this is a matrix B. Then trace AB. What's the definition of trace? Summation of diagonal entry, right? So now then when you do matrix multiplication, then first row in a matrix A times mean, actually dot product, right? Dot product of the first row of matrix A with the first column of the matrix B, that will return the what? First diagonal entry of matrix AB, right? What about second diagonal entry of matrix AB? Then we what? The dot product of the second row matrix A and the second column of the matrix B will return the second diagonal entry of matrix AB. Okay, so repeating this process, then we'll get all the diagonal entry, right? So which means that the what? The index of row in matrix A must be equal to what? Index of column in matrix B to get the what? Diagonal entry. Okay, so they see that I, J, J, I. So index of row in matrix A must be equal to must be what equal to the index of column. Okay, see that. So therefore we're gonna get the M diagonal entry because AB is M by M square matrix. Okay, so we get the so you know it's the AB11, AB22, AB33 through the AB and MM. Okay, so we're gonna get M diagonal entry, and then J goes 1 through N. But this, you know, the J goes 1 through N. We do that's the number of the columns matrix A, and then number of the row. I'm sorry, number of the row column. Yeah, number of the row in the matrix B. Okay, so that's what you understand. Yeah, here I'm sure that you understood this one. Okay, so now then what? But since the A B, I mean Aij and B sub Ji, these are just real number, so we can switch them, right? Because you're in the set of real number, the commutative properties are satisfied. So we can the you know you can change the order of the you know two numbers in the multiplicate with the multiplication operator, right? So now we just change it, but this is equal to what? Trace BA. Okay, what's the definition of trace BA? This. What's the definition of trace AB? This. Okay, but that two you know expressions equivalent, right? All right, second one, let A and B are square matrices and A is a real number. Okay, so then trace A is equal to trace A transpose. That's trivial, right? And the trace of A plus B is equal to trace A plus trace B. That's also trivial. And the trace A times A is equal to A times trace A. Yeah, that's obvious. So I'll just re-offset these three property without proving because these are pretty trivial. Third one, matrix derivative. Okay, the gradient submatrix A trace of AB is equal to B transpose. Okay, so here, before doing that, we assume that A is M by N matrix and the B is a M by M matrix. And then let's say F is the matrix valued function for mapping from R to the M by N to R. Okay. Now then let's then defined by that matrix value function F is defined by trace AB. Okay. Then gradient of submatrix A of F Ij. So I is a entry of that gradient sub A is by definition that is posure F or posure Aij, A sub Ij. So this is equal to posure or posure A sub Ij and then trace AB because definition of F is a trace AB. So this is equal to posure or posure A sub Ij, and then what's the definition of trace AB? We saw this one in the in here, right? You see it, this one. So this is gonna be AKL times BLK. Okay, so K goes from 1 through M, and L goes 1 through N because trace AB, A times B, the size of AB is what? M by M. M by M. So the K goes 1 through M. Okay, and the L goes 1 through N. Okay, so now then this one is equal to BJI. How come? Okay, So we take a partial derivative of this one with respect to aij. It means that only ij component will be left, right? All the terms gonna be gone. So if k is I and the L is j, then the partial AKL A sub KL times B sub LK with respect to AJ AIJ, that's gonna be what we can. That will be what if KI LJ. So we can say A sub KL is nothing but A sub IJ, then BJI. Then due to this one will be what BJI, which is BLK, right? Then all other terms gonna be 0. That's why BJI will be left, which is kind of coefficient of AKL. Okay. Yeah. So now you see that here. So but BJI. So I goes 1 through what? I goes 1 through M, and J goes 1 through N. Okay. So but here the order of the index is just the reverse, right? Comparing to this one, right? That's what we're going to get B transpose. Right? The second one, gradient A sub A transpose of F is equal to gradient sub matrix A of F transpose. Okay, so yeah, look at this. Gradient A transpose is this one. Okay, you see that? Instead of A sub, I switch the A sub 1 to A sub 2 1. Okay, in all other terms, I just switch. Okay. So that is equal to what? This is nothing but just the I told you we can get this one by switching the the index of row, index column in that gradient sub A, which is transpose of gradient sub A of F, without instead of the find the gradient of the A transpose. Okay, so instead of the just take a partial derivative of F with respect to the entry of A transpose, we just take a transpose of the gradient submatrix sub A of F, right? So that's why this is equal to this. Okay. Now next one. It means that what? If you take the transpose once again on both sides, then gradient of sub A transpose of F is a transpose of gradient sub A transpose is equal to gradient sub A of F. Okay, so that's keep in mind this. Okay, last one. That's the main part of this video. Listen carefully. This is quite probably you may find some challenge. Okay. The proof. Let's say f of A is A times B. So this f is the matrix value function, and then defined by A times B. So A is input, B is given, so it's fixed. Okay. And now let me define the capital letter F. Okay. So input is f of A. Okay. So and then D. Comma D. Okay, D is also input. This is defined by trace of f of A D transpose times C. Okay, so C is given. So it means that C is fixed. Okay. All right. So what is this? Okay, I introduced the lowercase f, which is a matrix value function. But what is this? Actually, this is a multivariable matrix value function. We haven't seen the multivariate calculus in vector calculus, right? Let's say f of input is this one has a multivariable real values x and y, and the output is x to dy. For example, again, this is one of the example of multivariable real value function. Okay. Now, and then let's say x and y are also real value functions. Simply, let's say x is t, y defined by t. Okay. So the x and y are parametric functions. We can say that. Okay. X of t is t, y of t is t. Okay. And then let's find out the derivative of f with respect to parameter t. Then we gotta apply the partial chain rule, right? Then partial f partial x, and the x is what? X is a function of t, right? So we have to multiply this one by the dx dt, and then partial f partial y and the dy dt. Okay, and calculating this, we're gonna get this one, right? So now then, let's just look at this. Okay, we applied this strategy into the proof. Okay. So now here, f is the multivariable matrix value functions. Okay. So now, okay, starting from this, gradient sub a trace ab a transpose c is equal to. Now you see that ab. Let's see. Give me a second. AB is the what? That's the definition of f of a, right? So this is equal to gradient sub a and trace of f of a. You make a trace of f of a times a transpose c, right? Okay. So now here, trace of a b a transpose c means that what? Trace of the matrix multiplication of these four matrices. Okay. Right. So now then, trace of f of a times a transpose c. Then considering D is a matrix A, okay, then we can express this one as the multivariable matrix value function, capital letter F, of f of A comma D. Here D represent A, okay? Okay. So now then, this is equal to, okay, then this is actually what? The partial derivative, right? Okay. Then this is equal to the, like what we did here. So we're gonna take a derivative of f with respect f of a, and then we take a derivative f with respect d. Okay, we'll just do that here. Right, I believe that you got it. So now then, the gradient sub f of a, and then multivariable matrix value function capital letter F times what? Because f of a is also a function of a, right? So we're gonna find the gradient sub a f of a. But we know this. What is this? This is gradient of sub a and trace ab, which is b transpose. We proved that, right? We need to prove that. And then the gradient sub f of a trace of this one, that's definition of capital letter F, right? Then that is equal to what? This is equal to A transpose C to transpose. Applying that property into here, considering D transpose C as matrix B, then we're going to get this one. But what about D? D is nothing but A, right? So that's I just replace D with A. So that's why we got this. Okay. All right. So now then, so the first term, it turns out that A transpose C transpose times B transpose. Okay. The second one term is this gradient sub matrix D, and then the multivariate matrix value function F, and then the gradient sub matrix AD. Okay. So now the gradient sub the trace of this, because that's a trace of this one. That's the definition of the function F, right? Okay. By the way, what is this? This is the identity matrix, right? Because D is nothing but A, right? So gradient sub matrix A of A is I, right? Okay, so then back to here. Then this is we got this one by definition of F, capital letter F, and then gradient sub D trace of this one, right? Because f of A, definition of f of A is A times B. Okay, so I just replace f of A by A times B. Now this one is equal to this one is equal to trace of this one. How come? Because trace of AB is equal to trace of BA. Right? That's we proved it, right? Okay. So now that's why we got this one. Okay. So considering AB is a one matrix and the D transpose C is another matrix. Okay, I switch them out, so we got this. Okay. Now then, that is equal to trace of that matrix to transpose, because transpose A is equal to transpose A transpose. A trace of A is equal to trace of A transpose. Sorry. Right. And then applying the transpose to the each matrices, we're gonna get this one. Because AB transpose is equal to B transpose times A transpose. When you apply transpose inside the parenthesis, then the order of the matrices will be reversed. Let's read this. Okay, so that is equal to then what? Then this is equal to this. I switched these two matrices, right? Because trace AB is equal to trace BA. Considering this one is one single matrix, this is another matrix. Okay, switch them. Then we get this. Okay. Now then what? Applying that property, we get the CAB transpose transpose. That's why we got the CAB. Right. So here, you may wonder that, okay, so then how about the size of matrices? Because you know, when you apply trace, that matrix must be a square matrix, right? So if A is m by n matrix, uh, then B must be n by n, and the A transpose must be, I mean, A is a m by n matrix, and A transpose must be n by m, right? Then B must be n by n, okay? And then C must be m by m, because that one must be square matrix, right? That's why C must be m by m, okay? So you see, applying the size of matrices for each into here, proof that it works. Okay, so we don't get any trouble about the size of any trouble for the size of matrix. Okay, so I proved that. Okay, so next time I'm gonna derive the closed form, which is a matrix form, uh, the cost function. Okay, so that's for today.